So for the Gorilla Glass question, what we're looking at is the durability of Gorilla Glass. The property of Gorilla Glass that's really special is when an object impacts it, some of the energy that goes into the glass actually helps to strengthen some of the intermolecular bonds. It actually makes the glass better able to survive that damage potentially that could happen to it. So in this question, they do something. If you watch the video, there's a lot of things they do to it. But we're looking at the video, the part of the video where they take a metal ball and they have a piece of Gorilla Glass down there and they drop it. It hits and then bounces part ways back up. The ball is 0.535 kilograms. That's actually a pretty significant mass. Half a kilogram is nothing to laugh at. And they drop it from an initial height of 1.8 meters. That's almost as tall as the roof in the classroom. So substantial height and pretty big mass hitting this piece of glass. It hits and then bounces back up after it was in contact for 0.30 seconds. This isn't the time to fall or anything like that. It's the moment of collision. It takes 0.30 seconds for the collision to occur. And then it bounces back up to a height of 1.1 meters. Now the first question is a two-parter. It says, when the ball initially strikes the glass after hitting, how fast is it moving? And then how fast is it moving when it initially bounces back up? Now what they're really looking at here is that as it falls, it's doing a classic sort of acceleration thing. And what I'm really looking at seeing happen here is that I dropped it from rest, and I want to find out how fast it's moving as it hits the glass down there. Its velocity isn't going to be zero when it hits there. It's going to be falling and faster and faster and faster, get up to the fastest it'll ever be falling. So VI is 0. My acceleration is negative 9.81, and it fell 1.8 meters, so that's got to have a negative sign also. You're going to be taking the square root of this. Negative times negative makes it so that we can handle it. VF equals, in this case, 5.9 meters per second. Now that's the number that comes out, but I should keep in mind the ball is falling, so that number, because of taking square roots and stuff, it has to be positive from the numbers, but it really is a negative velocity. It's coming down, strikes the glass, moving at 5.9 meters per second. I could also do this calculation if I wanted to, EP equals EK, because it starts with all potential at the top, changes into kinetic as it falls, all kinetic by the time it reaches the bottom. MGH equals 1/2 mv squared, cancel my m's, solve it, and you get that. Now notice 2GH, really, it's the same thing. It's why you'll still get the same number, 5.9, and then you'd have to put the negative sign on it for direction, but it still works out exactly the same. Now this is how fast is it moving at the moment that it collided with the glass, when it fell and hit. What I've got to do now is also figure out how fast is it going when it bounced back up off the glass. Now that's going to be different because it doesn't go back up to its original height. It only goes up 1.1 meters, and that makes sense because a little bit of energy is wasted. So what I'm going to do is take the VF squared equals VI squared formula and solve it for VI. So I would get something that looks a little clunky compared to what we usually see. It looked like that. Put in your square root. Now for this part, it's the moment from when it had eventually stopped and then it was thrown back up fast enough to actually get back up to that original, or not original, but the new height of only 1.1 meters. It's thrown back up. When it reaches its maximum height, it does have an instantaneous velocity at that point of 0. I'm going to throw in my negative gravity there, and it went up a positive height of 1.1. This is going to work because I'm subtracting negative stuff, so it's going to be positive. I can take a square root, I can do all that stuff. I find that as the ball came back up off of the glass, it must have done it at 4.6 meters per second, positive, as it came up off of the glass. It hit coming down faster, but it only gets thrown up at 4.6 because it's not going to go as high. I want to determine the impulse that was acting on this ball now if this is what happened during the collision. I'm not going to use F delta T equals M delta V because I distinctly want the impulse, so I had to snap my formula in half and get this. I know the mass of the ball, 0.535 kilograms. I have to always make sure that I'm doing those masses in kilograms. Final minus initial. Now this is where it's kind of weird because when I did this, this was final, and I did this, this was initial. But this is the end of the question, 4.6, and this was earlier in the question, negative 5.9. So I actually have to kind of flip them around because of, even though what I had to do in these formulas, this was earlier in the question, this was later in the question. So final minus initial works out that way. I'm going to take 4.6 really plus 5.9 times the mass, and I come up with an impulse of positive 5.7 Newton seconds. Or you could write in kilogram meters per second, it would still be equivalent, okay? So that gives me an idea of the impulse that acted on the glass. Determine the force that this exerted on the glass. I have my impulse. I can solve the other half of the formula to say that I know the impulse that was acting, which I should mention, it's acting upwards, because if something comes down and then is going to get pushed back up, the impulse has to be positive that whole time to get rid of its negative momentum and end up giving it some positive momentum on the way back up. Back to here though, the time, 0.30 seconds, gives me 19 newtons of force. That's how much is actually exerted on it during that collision event. That's actually a significant amount of force acting on a thin piece of glass. Now the last question that's down here says, a friend asks if changing the glass so that the ball bounces all the way back up would be better. Now the argument they have is that would mean the ball would carry back all of its kinetic energy to be able to get back up to its original height. Now that on the surface sounds like a good idea, but it's actually worse. Because think of it this way. If we actually cause the ball to go back up to its original height of 1.8 meters, this wouldn't be 4.6. It would be positive 5.9, because it would take just as much velocity in the positive direction to get it back up to the 1.8 meters. So this would be positive 5.9. This would be positive 5.9. That would mean that because I've made the delta V actually bigger, if you do the numbers on it, that makes delta V bigger, delta P would be bigger. There would be more impulse needed. If the impulse has increased here, so would the force. You're actually going to potentially cause more damage to the glass. So minimizing this, actually, if we could, we want the ball to hit and not bounce back up at all. That would mean this would be 0. This would be 0. This would be the smallest it could be, and this would be the smallest it could be. That would be the best deal.